Okay, so this lesson is for Monday, January, I don't know, 27th, I think. And so you were around Thursday and Friday, most of you. So I want to point out some things. First of all, the notes for last week are here in Google Classroom, including all of the work that we did in class. So if you need to make something up, or you have a question, or you have to clarify, you can check this out. Whoops. It goes all the way through the stuff we were doing Friday. So if you weren't here for something or you didn't had a question, we're going to deal with that now. So let's pull this up. So I'm going to go, that was week 3-1. Now some of that stuff is also in this week 3-2, which we are going to look at. So it's also in here. We did 12 to 14 on a video lesson. It was done for you. All you had to do is get the book out, read the questions, get a paper out, and literally write down what I have and turn it in. So I have had students, multiple students, ask me about a grade or email me about some work that they missed, and then they didn't do it. So that I have hours of my week wasted by other people. That isn't the thing that I find exasperating. The thing that I find exasperating is, why did you email me, ask me about it, and then not do it anyway? You weren't going to do it anyway, so why did you waste your own time to send me an email or worry about it enough to ask me, and then not do it work that I have pretty much done for you? All that's documented. All of that is, it's online. I have students that haven't turned anything in or not turned some things in. It's online, it's there. I can document all of this. So when, somebody comes in and we want to have a discussion, after I show them it's all there, then they're going to have to start calling names because they don't have a good argument. So keep that in mind. It happens. All right, so let's go over the ones on Friday that I gave you to do. Because Thursday you had about 12 minutes worth of work or so. Friday you had about 15, 16 minutes worth of work or so, which meant you had a whole period there to have other people help you get caught up, including us up. So there was time. I can document that there was time. Let's look at page 55. So your book should be opening up. And you should have the paper out. If the paper's not out, pause, get the paper back from the sub, and let's go over this from Friday on page 55. Okay, question 16. Describe a car's velocity as it goes around a track at a constant speed. Well, its direction is changing. So the magnitude, in other words, is the magnitude of the velocity. The speed stays the same. It doesn't, the fastness of it doesn't change. The direction changes. And that means there's an acceleration. And the way you can tell is you'll feel forces pushing on you. So if you're going around a curve, it feels like you have forces pushing on you. So you know you're accelerating. And if you're accelerating, that means you're changing your direction and you're changing your velocity. So later on, we aren't in this class going to do calculations on changing velocity or changing direction. We'll talk about it. We aren't going to do calculations. That's for physics. We will talk about, in a straight line, changing your speed. We're going to have one equation for that we're going to look at. So this car is accelerating because its velocity is changing. 17. Why do they have speed limits rather than velocity limits? Well, because you're going to follow the highway, hopefully, and stay between the lines, and that's the direction you're going to go. If you were an airplane, you'd have to map this out and follow it. So velocity includes direction, so a velocity limit would limit the direction, and the car is going to change the direction with the road. It's going to go up, down, and left and right. So you could pause this and write this down and improve your answer if you wanted. Okay, 18. For each of the following news stories, determine whether the object's speed or velocity is given. World record for the 100-meter dash is 10 meters per second. They don't care if you're running north, west, south, or east, or which hemisphere you're running in. You're just running the speed. Usually it doesn't matter unless it's windy and it's outside, then it would matter. World record, the wind today is 30 kilometers per hour from the northwest. Okay, that's a speed and a direction. That is a velocity. C, well, it's not C. A 200,000 kilogram train traveling north at 70 kilometers per hour is a speed and a direction. So that is a velocity. And next, a car was issued a ticket for traveling a certain speed. Now, no direction was given here on the police officer's report or highway patrolman's report. It might say you were northbound or southbound or something. But in this case, it was only the speed that was given. Okay, 19. You're walking towards the back of a bus that's moving forward at a constant velocity. Describe your bus. Well, motion relative to the bus and the ground. If the bus is going this way and you're going this way and you're going the same speed, you're both going slow, it would look like you were over the same point on the ground. So it is the speed of the bus minus your walking speed. One's positive, one's negative. It's really a number line problem, and we talked about those last week. Well, the week before last. So if the bus is going, let's say the bus is going 10, and you're going 2 meters per second, and somebody's out here watching you go by, how fast would it look like you're whizzing by? So relative to the bus, you move backward at your walking speed. So you're going past the seats and everything at walking speed. But relative to the ground, you're going the bus's speed minus your walking speed. So if the bus is moving faster, you're still going this way. If you jumped out of the bus, you'd tumble down the road this way, but not as fast. You will move in the direction of the bus. If the bus was slower, you would move in the direction that you're walking. Okay, back to my question. If the bus is going 10 this way and you're going 2 this way, your observer, your speed compared to this observer would be 8 meters per second. Number 20, what is the momentum? So you need a calculation here. And by the way, most students are being champs about this and stepping up. Let's try to keep that picture in focus. Okay, it's not that hard though. So if it's not that hard and you're dropping the ball and creating time wasting problems for me to deal with. Exasperating. Okay, so here's the equation, mass times velocity. You just have to calculate it. There was problem 12, 13, 14, and 15 that I did for you on that one video. That's still up there. You were doing this calculation. So you put 100 kilogram football player, yes, here, and the speed and direction here, which is 4 meters per second. And you just multiply these and keep two things. The unit, which is going to be kilograms times meters per second, and the direction. So it's going to be 400 kilograms times meters per second north. No, let me just randomly grab, I could randomly grab some papers and see if students did this. Hopefully you have enough conscientiousness to give that a reasonably good attempt. The next one, I didn't look at that one so much. The next one I looked at on some papers, and it's a momentum equation. It says compare the momentums. So I'm going to introduce a symbol that you've never seen before that I use, that I made up, but I've seen it other places too. Are these equal? And so you have an elephant and a dolphin. They're momentums. You got an equation for one, you got an equation for two, you got to calculate both of these. And so the way I set this up was mass times velocity. Is this equal to the other mass times velocity? So if you just wrote a number down for the answer and some 1-word or 2-word or 3-word responses for the other questions, And you want to tell me that took you 45 minutes and you didn't have time to make up other work that you got missing? Come on. So what I'm doing is this equal? So I have an elephant that weighs 6,300 kilograms. Remember, this is mass times velocity. And this is mass times velocity. We want to know if these two are equal. And the elephant is moving at 0.11 meters per second, which is this far in a second, 11 centimeters. Moving pretty slow. And a dolphin is moving 50 kilograms, but is going 10.4 meters per second, faster than any of us can run. This is like world-class sprinter would not, at their peak speed, would be going maybe that fast. And the elephant comes out to 693, and the dolphin comes out to 520. So they are not equal. In fact, who's got more momentum? The elephant has greater momentum. So if that's not your answer while you're looking at your paper there, correct that. And you should have two calculations. This one and that one, not a one number answer written down. Come on. Okay, I wanted to go through that. Next, let's talk about acceleration. And what acceleration is a change in what? It is a change in velocity. And you can get there different ways. You can speed up, slow down, change direction. So you can change your speed up or slow down. You can change your direction, or you can change both. You know, hit the gas and turn. Hit the brake and turn. That's changing both your speed and direction. Pretty simple concept. So acceleration is a change in velocity, change in speed or direction, and how quickly that's happening. If it's happening in a short period of time or a longer period of time. Okay, I want to show you a video of a guy, Felix Baumgartner, this is probably 15 years ago, jumping from a high altitude balloon, maybe 100, I think it was like 120,000 feet up, it was like 20 miles up. This guy's out of most of the atmosphere actually. And he's gonna jump off this balloon and there's not air resistance. So in a span of about 30 seconds, he gets faster than the speed of sound. And then actually gets into thicker air and slows down. So he goes supersonic here. Let's give this a watch. Oops, here we go. And within a few seconds, he's already gone 100 miles an hour. He's up so high, it's a big fisheye lens, but you can see some of the curvatures of the Earth too. He's up so high. Okay, he's probably 20 seconds in by now. That's the balloon up and above him. His camera's showing above him in the sun. And there's hardly any air, not enough to really make a spacesuit do this. By now, he's probably going supersonic. He's going 600-700 miles an hour by now, 30 seconds in. And then he starts to get into enough air that sets him up to start spinning. And you can start to see the air moving his suit just a little bit, just enough atmosphere to move his suit. Now he's spinning at a deadly rate. This is dangerous at this point.
What is he doing?
This is the guy that held the previous record. He's there helping Felix set a new record.
But he's lost control.
Skipping ahead. So he's been falling now for about a minute and a half. He's probably slowing down at this point because the atmosphere is getting thicker. So he pulls the parachute here, stops his spin, but he's pulled the parachute now, and he makes it back and sets the record. Okay, that's the end of this video. See you on the next one.